Hi, in this session we are going to talk about conductors and dielectrics. Let me give you a brief context here. So far what we've done is, in electrostatics, we have seen that a charge distribution causes electric field. We can also find out the force between two charges using Coulomb's law, and we also learned about concepts like potential, dipole, etc. So far in our inquiry, what we have done is, we have seen how if charges are separated by each other with a certain distance, and how if those charges, we know the magnitudes of them, we can calculate electric fields, or we can also find out the forces due to those charges. Specifically, the basic example that we took was of the Coulomb's law, which gives us the force between two charges if they're separated at a distance r. We said that the force looks something like K Q1 Q2 upon r square, where r is the separation. Here we have seen how if Q1 varies, Q2 varies and r varies, the force varies. What we are going to do in this session is have a better look at K. K, we have seen it is also written as 1 upon 4 pi epsilon naught when these charges are kept in a free space medium. So K is essentially the property of the medium in which these charges are kept. When in the standard assumption we write this equation, we say that the medium is free space or vacuum. Now what we are going to do is, we will think, what if the medium was not vacuum? What if the medium was something else? Maybe a solid block of some metal, or say water, if the two charges are kept in water. What happens to this particular constant? So we had a brief discussion wherein we said that this epsilon naught is the property of free space or vacuum. For any other medium, we will use this constant epsilon, which will be that property. This property's name is permittivity of that particular material. Now to do this, we are going to follow a specific line of inquiry in our discussion. That line of inquiry is this. What we will do is, we will assume that there is an electric field in free space, and then we will keep some material in that free space. Then we will see how does that material behave. Is there any difference in the inner structure of those materials in terms of the atoms, the electrons and the protons? Do they get distorted? And then we will see that how different materials behave there gives us some clue about this particular quantity. So this is how the entire scheme will look like. We will define the space like this coordinate system that we have, and this is the block of a material. Now, if you consider this particular diagram here, which is drawn, you can see that this material could either be a solid. If you want to generalize things, then the matter can exist in either solid, liquid, or gas form. And then we will further narrow down our inquiry. What we will say is that in this discussion, we will not study about gases, because gases are in themselves inert. Their atomic structure is completed. They do not interact with the environment much, and you've seen that there are noble gases like xenon, radon, so they don't have much effect on electrostatics. So this is something that we're not going to study in our course. Liquids, will say that they behave almost like solids. So it is the solids that we are going to focus much on. And even among solids, we can say that there are three kinds of solids when we inquire in the line that we are doing right now, that is exposing this solid material block to an electric field. In this context, a solid can be categorized as either a conductor or a semiconductor or an insulator. And insulators, we will see that they also have another name called dielectrics. So I'll write insulator, and then they can also be called as dielectrics. So Now, let's see what is the difference between a conductor, a semiconductor, and an insulator or a dielectric. So let's say if we have an atom of each of these kinds of materials. So a typical atom of a conductor looks something like this. Here we have a sodium atom. You can see that if we consider only the outermost shell, you will see that there is only one electron, and then we say that this electron, because it is in the outermost shell, it does not feel much attraction by the nucleus. So if there is any other external force, it might get freed from this atomic structure and it would be free to move if certain forces are provided and certain situations are maintained. So that's the basic atomic structure of a conductor. Then if we look at a semiconductor, let's take a silicon atom here. You can see that there are 4 electrons in this outermost shell. This outermost shell, by the way, is also called valence shell. Then you can see because there are 4 electrons, there is more force of attraction, the radius of the shell has decreased and it is more tightly held. However, if you increase the temperature, you can still free some electrons and they might be free to move in that material itself. Similarly, if you look at insulators, you will see that the electrons here are even more tightly held and they're almost not free to move. So this is how we can visualize the atoms of these individual types of materials, the conductor, the semiconductor, or the insulator. Let's see how these properties manifest in the macroscopic object. We will refer back to our scheme here. In our line of inquiry, we have this space where there is some electric field and then there is a block kept here. Now, before moving ahead, let's say we will see that semiconductors, because they have intermediate number of electrons, they behave sometimes like conductors. When the temperature is high, we have more free electrons. When the temperature is low, they behave like insulators. They don't have free electrons. So in our chapter, in this particular session, we will not discuss much about semiconductors because they have intermediate properties of conductors and insulators. In this session, we will devote more time to know these extreme properties, and then the intermediate properties we will learn in some other chapter. So right now we will focus on conductors and insulators. So yeah, let's get back to the scheme here. Now if this block, let's say if it is made of conductors, we've seen the atomic structure. In the atomic structure, we felt that there are a number of free electrons which might move across this block in this macroscopic manifestation. So if there is an electric field applied, these free electrons will feel a force due to this electric field. And you can see that the electrons always feel the force in the direction opposite to the electric field. So what will happen is, if the electric field direction is such, the electron's force direction will be this. And due to this, these electrons will start moving. They're free to move in this macroscopic object. And due to this, what is happening is these electrons have started accumulating in this particular phase of the block. And as such, this particular phase has now an excess of electrons over protons and it is negatively charged. What happens to the farther phase? You can see that in the farther phase, there is a deficit of electrons because electrons have moved from there till the next phase, and hence there will be positive charge that will be figuring out in that particular phase. Also, till when will this movement of electrons keep happening? Now, you will notice that if you want to find out the electric field at any particular point in this particular block, that electric field can be found out by the superposition of two fields. Let's say the net electric field right now at this point is E, then E is a vector sum of two fields. One is E naught. E naught is the external field like here. And then because of this movement of electrons in these two walls, there is an induced field. This is a field that has been created. It was not externally applied to this block, but this block's electrons moved and aligned themselves in such a way that it is a charge distribution in itself, right? And a charge distribution will give you some electric field. So this is induced electric field here. And you can see from this diagram that if the charge distribution is such, that is the positive side of the block and this one is the negative side of the block. So the angle that the external field makes with the induced field is that of 180 degrees, as in they are in opposite directions. So if we write in terms of scalar, the net electric field at any point will be given as E naught minus E induced. Now the question that we were trying to find answer to is till what point the electrons will be moving in the left side of this particular block. The answer is so long as there is some resultant field, right? Because if there is resultant field, then electrons are feeling the force given by Q times E. So that particular movement will keep on happening, and it will keep on happening till the point that the charge distribution has become such that E naught has become equal to, E induced has now become equal to E naught, and in that case, the electric field at any particular point on this block becomes equal to E naught minus E naught, which is 0. So that always holds true for a conductor. I will repeat the statement. For a conductor, whenever it is subjected to any external field, what happens is there is an induced electric field due to the alignment of electrons in different phases, and as such, the resultant electric field at any particular point of the conductor, it becomes equal to 0. Now you can see from the treatment of this particular concept, we haven't used the geometry of this object anywhere. So this result must hold true for all geometries. We have done this generalization that for any conductor, be it of any shape, it might be a block, it might be a spherical shell, or it might be a ball or a sphere. For any particular shape, electric field inside that conductor is going to be 0. This is a pretty interesting result that we have obtained. I will write it holds true for conductors. And we will see that this particular property has so many functionalities, and because of that, there are so many applications that can be generated. So all this will come in due time. For now, let's change our object in place of conductors. This time, let's say we have an insulator or a dielectric. So we saw an atom of an insulator or a dielectric. We saw that there was some positive charge concentrated in the nucleus and there was some negative charge in forms of the electrons that were in the shells. So it is like this situation that although presently there is negative charge and positive charge which are not together, but the center of both these charges is together. So this kind of an arrangement in macroscopic sense, it manifests like this. This time the block is made up of an insulator, not a conductor, and you can see that we have these spheres representing that these may be atoms or molecules, where positive and negative charge inside these spheres, individual spheres, are uniformly distributed. Now, let's switch on the electric field in this region. As soon as we switch on the electric field, we know that the negative charge will behave in a manner different than the positive charge. The negative charge is feeling force in this direction, and the positive charge is feeling force in the other direction. So you can see that the individual poles, you can call it a dipole now, these dipoles have been formed now. You can see the negative charge is such and the positive charge is such. As a result of this, what is happening is, although there were no free electrons to move in the case of an insulator or a dielectric, however, if you consider at the molecular or atomic level, there is further some splitting of negative and positive charge, and it manifests itself as dipoles. So although there will be not absolute movement of these electrons and hence the negative charge, there will be some movement of negative charge towards this phase, and consequently there will be some positive charge in the opposite phase. You can see the diagram looks something like this. Eventually you have negative charge in this phase and the positive charge in that phase. However, this time the motion doesn't stop at this condition where the induced electric field has become equal to E naught, because the internal electrostatic forces between the nucleus and the valence electrons, they are also significant in these particular cases. So the motion stops before this situation is reached. In fact, we can define this particular property of any dielectric material by a constant known as dielectric constant. So dielectric constant, we will use symbol K for it. It is defined as such that the expression for E induced in terms of E naught or the external electric field can be written as E naught into 1 minus 1 upon K. Remember to note the difference between this capital K, which is the dielectric constant, and this small k, which is the constant of proportionality in Coulomb's law. These two are different quantities. So this is the relation that we get. Now, let's say if you want to find out what is the dielectric constant of a conductor, you notice in this formula, if you put K equals infinity, this term 1 upon K goes to 0, and you get E induced equals E naught in the steady state. And this was what the result was when we had obtained it. Similarly, if you put vacuum, if there is nothing, then it has a dielectric constant of 1. In that case, the result that you get is E induced is equal to E naught 1 minus 1, which is there is no induced electric field, there is only this external electric field. So we've got this limit for vacuum. We have K equals 1 and hence no induced electric field. For a conductor, we have K tending to infinity. It has a very large dielectric constant, and then the induced electric field becomes equal to E naught itself, making the resultant electric field as 0. Now, if you notice that neither a vacuum, which is the absence of any material, or a conductor, none of them is a dielectric itself. So the typical value of dielectric constants for real dielectric or insulating materials, it varies between these two extreme limits. We have just derived these limits to get the numerical feel of what the value can vary in between of this dielectric constant. And let's say we have some other material having some finite dielectric constant between 1 and infinity. Then our formula for the net electric field given by this particular equation here, E is equal to E naught minus E induced. Let's try to find out what E comes as the result of this formula. I'll write for dielectrics I have E given as E naught minus E induced, and E induced is minus E naught 1 minus 1 upon K. This gives me the formula. If I take this bracket inside, I'll get E naught upon K as the net electric field inside any dielectric medium. So now we have generalized this equation. If you notice, we had started from this Coulomb's law's equation where we saw that we have not so far considered what is the effect of this constant of proportionality. Is it dependent on other things? We found out, or rather reasoned, that it depends on the medium in which these charges are kept. And then we said that so far we have learned how to calculate the Coulomb's law or forces due to them only for the case when the charges are kept in vacuum. What we wanted to do was, we wanted to calculate the forces when these charges were kept in other mediums. Then to do that, we followed this line of inquiry. We did a thought experiment wherein in our space, in our free space where there was some electric field given as E naught, we took a block of object and we considered two specific cases for now, conductors and insulators, both solids. In those cases, we found out that if we want to get into this form of equation, we can define this constant known as dielectric constant, and then the total electric field or the resultant electric field at any point inside this medium will be given as E naught upon K. So this kind of finishes our discussion about what effect the medium will have. What it will do is, it will modify the electric field if E naught is the external electric field in this sense, and then if you put in the values in a conductor, if you are considering a conductor, then E becomes E naught upon infinity, which is 0. So in a conductor, this relation always holds true. We will see it in a big way in coming sessions. Then if you take vacuum, then you have E equals E naught, which is the standard relation. Now, I also told you that K can be expressed as 1 upon 4 pi epsilon for any other particular medium, where E is the permittivity of the material or the medium. I think it will be worthwhile to do this little exercise wherein we equate the electric field taking this particular form of equation and taking this equation, and then how about trying to find out the relation between E and K. Let's do this small exercise. So in this exercise, let's assume we have a point charge with us. I'll depict the charge like this, and let's say the magnitude is Q. Then at any particular point, let's say I denote this point as O, let this be the location of this charge A. Then if I say that AO is R, then the electric field, and now by the way I'm assuming that right now the medium is not vacuum, it's some other medium. Let's say it has permittivity epsilon, and the other way to describe this medium is through its dielectric constant, which is capital K. So we will interchangeably describe them using both of these equations. So this says that if I want to find out the electric field here, if you use epsilon as the expression, the electric field becomes equal to only the magnitude I'm talking about right now. So it is KQ upon R square, and K this time is 1 upon 4 pi epsilon. I'll just expand this equation. Q upon R square. Then let's try to find out the electric field by this method. This method says first find E naught, that is assume that the medium is not this particular medium but vacuum or free space. So in that case, E naught will become equal to 1 upon 4 pi epsilon naught Q upon R square. The form of the equation doesn't change, right? It's only this constant that has changed. And then if I want to find out E, which is E naught upon K, I have to simply multiply this denominator with a K. So I get E naught upon K in this sense. So these two things should really be equal, because both of them are giving us the expression for E, and if you equate them, you find that the other terms are same. The only term that differ is that there is an epsilon here, and here we have a K and an epsilon naught. So if you equate these two expressions, what you get is epsilon equals K into epsilon naught. And then another way to express this is epsilon upon epsilon naught equals K. And then you would have seen this form many times. Some property upon some property in the vacuum. This is called the relative. We use this adjective relative. For example, if you're talking about permittivity, permittivity in a medium upon permittivity in vacuum is called the relative permittivity of that medium. We saw similar form when we were studying about optics. We saw absolute refractive index and then relative refractive index. So it's that kind of a thing. So we can use another symbol to denote this. Let's call it as ER. So this is a very important relation that we've obtained, that K is equal to ER. So if I were to speak this relation in simple English language, I would say that the dielectric constant of a material is equal to the relative permittivity of that material with respect to vacuum. So these are two terms we've seen that they are closely related to each other, this term permittivity and the dielectric constant. And we've also seen in this particular session that how do different materials behave. when they're exposed to this electric field. Now, what we've done is, we have done this inquiry from the point of view of finding the properties of the medium in which the charges are kept. Another perspective here, with the same thought experiment, could be how a material is polarized. You can see that in this material, what essentially happened was, it was neutral through and through, it was uniformly neutral. However, whenever an external electric field was applied here, you saw that one of the phases acquired negative charge and the opposite phase acquired positive charge. So you can see that there has been some polarization that has happened. There's a pole of negative charges in this phase and the pole of positive charges in this phase. So I'll just write this keyword polarization. You will see its application also in a later session. I think it's worthwhile to introduce it here. This is called polarization. And this wraps up this session.